If you are a designer, you can probably relate to this story very well. You've just finished your first big circuit board design. The prototype works beautifully in the lab, and the software runs, the power rails are clean. You are feeling really, really good about this. You're going to nail it on the first try. And then there's that moment of truth. It's compliance testing. And that's when everything goes awry and turns into four-letter words. Suddenly, emissions are off the charts. The compliance lab tells you that your device is radiating like a small radio transmitter. Or worse, when they point a big antenna at it, your board suddenly locks up and it stops responding. Now, if this has happened to you, trust me, you're not alone. It's actually one of the more common first brick wall experiences for a design engineer. And the culprit is electromagnetic compatibility, or EMC. So today we are going to talk about one of the most powerful tools in your EMC toolkit, and one that is really underrated, and it's shielding. So by the end of this episode, you're going to know what shielding is, how it works, the jargon you're going to need to use it confidently, and the most common pitfalls that beginners run into. You're listening to Würth Elektronik's What's Up, a radio podcast where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, and today, an introduction to shielding. So tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. Right off the bat, we are going to start simple. EMC, or electromagnetic compatibility. This means that your product can live peacefully in its environment. So in other words, it's not going to emit so much interference that it's going to bother other devices, and it's not so fragile that the outside noise causes it to fail. Shielding is one of the most straightforward tools that we have to tackle EMC. At its heart, shielding is about containing fields. If your device is noisy, shielding keeps those fields inside. And if the world outside is noisy, shielding keeps those fields out. Think of the Faraday cage, named after Michael Faraday, and in his 1843 ice pail experiment, he actually lowered a charged brass ball into a metal ice bucket without touching it, and then used an electroscope to show that the charge immediately migrated to the outside of the bucket, leaving no field inside. This experiment actually proved that electric charges resides only on a conductor's exterior surface and that the interior is completely shielded. And that simple insight still underpins shielding today. But in the real world, our boxes are not perfect. We have seams, connectors, vents, displays, various plastic parts, and shielding effectiveness depends not on just throwing some metal around a board, but on the very specific minute details, the material, the thickness, the openings, the way you tie it into your grounding system, and the way it's placed on the board overall. Every single electronic device is both a potential source of interference, but it's also a potential victim of it. Digital switching and semiconductors, poor PCB layout, bad grounding, all of these can actually generate noise. And at the same time, things like electrostatic discharge, radiated fields, or power line noise that can all enter your system and cause it to misbehave. Now, this doesn't mean that every product needs shielding. In fact, a low-speed microcontroller running at 1 megahertz with no long cables, something like that might never require it. But once the clock's pushed past tens of megahertz, or there are cables longer than half a meter, that is where shielding comes into play. So here are a few rules that you could follow when shielding might be essential. First, if your circuit radiates strongly in differential mode, you'll need shielding to meet these limits. Second, if your product is going into noisy environments like industrial or medical, then shielding is a must. If your design has several shielded cables plugging into it, Then a shielded enclosure is probably essential. And finally, if your PCB already has solid ground planes, you may only need localized shielding around critical areas. So a good engineer asks the shielding questions early in the project. But again, as a design engineer, we've all been here. And waiting until after a compliance failure usually means that your options are very limited and potentially expensive. Now, quite often, you'll hear EMC engineers talk about SE, and this is shielding effectiveness. It's measured in decibels, just like gain or attenuation. Formally, SE is the ratio between the field strength without shielding and the field strength with shielding. The higher the number, the better the shield. Shielding effectiveness comes from three components. First, reflection loss, or R. This is the wave bouncing off the surface of your shield. Highly conductive materials like copper and aluminum are great at this, especially against electric fields. Think of it like shining a flashlight in a mirror. Most of the light never even gets inside. Reflection usually dominates above 30 megahertz. Second, absorption loss, or A. And this is the energy that does make it into the shield material, but then dies out as it travels through. Steel, for example, is better at absorbing magnetic fields than aluminum. Absorption becomes significant above roughly 100 megahertz as skin depth shrinks and energy dies out faster. And then third, there is back reflection loss, or B. Now, if the shield is thin, the wave that slips through the front surface can bounce off the back surface and reflect inside the material and partially cancel itself out. It's like echoes interfering inside a thin wall. In practice, this only adds noticeable attenuation for thin foils or coatings at lower frequency, but it's part of the complete picture. So when we're talking about a shield having 80 decibels of effectiveness, what we really mean is the sum of all three: reflection, absorption, and a little bit of back reflection. But of course, it can't just be that easy. Close to a noise source, like a switching regulator, the fields don't behave like clean radio waves. One part dominates, either electric or magnetic. And in this near field, the wave impedance can actually swing high or low, and that changes how well a shield works. High voltage with low current means the electric field dominates. Low voltage with high current means the magnetic field dominates. Farther out, the fields settle into a plane wave with a fixed impedance of 377 ohms. That's the so-called impedance of free space. And that's important because it means that shielding is predictable in the far field. In the near field, though, the impedance could be very different. So you need to know if you're fighting electric fields or magnetic fields. And that's why thin aluminum is really great for electric fields. But if you're dealing with low-frequency magnetic fields, composite, like the WE EMI patch from Würth Elektronik, that is a flexible adhesive sheet with both a metal and magnetic absorbing layer, and that can give you broadband shielding in a compact form. So I just mentioned that the WE EMI patch from Würth Elektronik was made of a composite. But let's talk about the stuff that the shields are really made of. Metals are the classic choice. We have copper and aluminum, and those are really great for reflecting electric fields thanks to their high conductivity. Then steel and other ferromagnetic materials are better for absorbing magnetic fields, especially at lower frequencies. But as you know, designing isn't just about physics. It's also about the weight, the cost, manufacturability, and the reliability. A thick copper enclosure would really be fantastic, but they're also heavy and very expensive. And that's why composites and plastics with conductive coatings are often used. By adding fillers like graphite flakes, metal-coated fibers, or conductive coatings, you can give a plastic housing reasonable shielding properties. And here's a practical point that engineers sometimes overlook: corrosion. It's not just about conductivity today. It's about how the shield holds up over years and years in the field. Corrosion can ruin shielding performance faster than a poor material choice. So what other weak points should we actually point out? Well, here's the thing about shielding. The shield itself is rarely the problem. The weak spots are almost always the openings, the seams, the slots, ventilation holes, and connectors. So think of it like a soundproofing room. There's a very thick wall, you have the insulation up, but it's absolutely useless if you leave the door open an inch. And that's the same with shields. One long seam or slot can act like an antenna. And that's why engineers use conductive solutions to close those gaps. For instance, Würth Elektronik's WELT is a conductive shielding gasket. This is a self-adhesive foam strip wrapped in conductive fabric. It lets you seal seams and maintain electrical continuity even when covers or panels shift in production. And that makes a big difference for maintaining real-world shielding. So the takeaway is really quite simple. Your shield is only as strong as its weakest opening. So now let's take a look at design integration. We're going to zoom into the board and system level. At the PCB level, shielding cans can be soldered over noisy sections. Even more powerful is to actually design solid ground planes into your layout. And that's because those planes provide both shielding and low impedance return paths. At the system level, cable terminations are a huge deal. Now, if you've ever seen a shielded cable with the braid folded back and tied to the ground with a little pigtail wire, what you've just witnessed is a failure waiting to happen because that little wire adds inductance, and at high frequency, it basically disconnects the shield. Now, the correct way to do this is 360-degree termination, where the shield braid makes full contact with the connector shell, and that shell makes full contact with the chassis. So in effect, the cable shield becomes an extension of the enclosure. The whole point is to give surface currents a continuous, low impedance path. If the shield continuity is broken, those currents will find other paths, and that usually means radiation. Now, if you haven't been taking notes, now is the time to do so. Maybe push pause until you can get to a pen and paper, because we are going to talk about some common beginner mistakes. And these are traps that we see the beginners fall into. Ready? Okay. First, assuming thicker metal is always better. At high frequencies, skin depth dominates, so doubling thickness doesn't necessarily mean double performance. Second, ignoring seams and connectors. A beautiful, thick enclosure with a sloppy cover seam that can leak like a sieve. Third, adding shielding too late. Now, if you treat shielding like a last-minute Band-Aid after a compliance failure, you'll often find that you cannot fix the problem without having to do a brand new major redesign. And the fourth major beginner mistake is over-relying on one approach. Now, shielding is powerful, but it's not magic. It works best when combined with good PCB layout, filtering, and grounding practices. So let's recap what we've learned today. First, shielding is about containing fields. It protects both your devices and its neighbors. Next, effectiveness comes from reflection, absorption, and back reflection. Third, materials matter. Copper, aluminum, steel, plastics with coatings, but so do cost and long-term reliability. All of that matters. Next, openings are the weak link. The smaller and fewer, the better. Also, integration is key. Good PCB layout, solid ground planes, proper gasket, and also cable termination. All of those multiply the value of shielding. And finally, test early. Don't wait for the compliance lab to tell you that your product is a radio transmitter. So if you are a new engineer or a student wanting to impress your professor and you're facing your first EMC shielding challenge, just remember these tips. Design for continuity, minimize openings, and think about shielding from the start. If you do that, then shielding becomes a tool that you control and not a patch you slap on later. If you're looking for more tips on shielding or wondering how we got all of our wonderful information mentioned in today's episode, we encourage you to read our new design guide, ABC of Shielding. You can order this reference guide with your local Würth Elektronik sales representative or online at www.we-online.com. While there, you can sample EMC shielding components, including the WE-LT, conductive shielding gasket, or the WE-EMIP, EMI patch mentioned in today's episode. We also encourage you to sample other EMC components, including ferrites, line filters, chokes, and more, online at www.we-online.com. Again, you can reach out to your Würth Elektronik contact, chat with the live team at Würth Elektronik Online, or even order directly through the new MyWE customer portal. You're listening to Würth Elektronik's What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.